Hello, this is Richard Collins, your instructor in ATM 101 Weather and Climate of Alaska here at the University of Alaska Fairbanks. Today I want to talk about Problem 2 in the second practice exam. The topic of Problem 2 is wind, how it's generated, and the forces that determine its strength and direction in the atmosphere. Question A. Which of the following forces causes a stationary air parcel to begin to move horizontally? The answer is 2, the pressure gradient force. Changes of pressure with distance, pressure gradients, are what cause the wind to be generated, that cause air parcels to begin to move in the atmosphere. The theory behind this as we go through the problem is that differences in heating cause temperature differences in the atmosphere. Temperature differences give rise to pressure differences, and it's pressure differences that drive the wind. This is the mechanism by which the wind is generated. The general principle of energy transfer is that energy is transferred from hot areas to cold areas. Therefore, the mechanism that we're looking at is how that plays out in the atmosphere. That general principle, warm air travels to regions with colder air and carries its heat with it as the basic energy transfer in the atmosphere. Question B. Two columns of air are located at warm and cold locations, as shown in Figure 2a. Which best describes the physical situation? And the correct answer is the warm column expands more than the cold air column. There is a higher pressure at a given height in the warm column. There is a pressure gradient force from the warm column to the cold column. The answer is 2, and the picture is the middle panel of Figure 2a, where we see a tall red column on the right and a short blue column on the left. The pressure halfway up the column is 500 millibars. That pressure is higher in the red column than in the blue column, so that if I travel at an altitude in the red column, from the red column to the blue column, I'm going from a higher pressure to a lower pressure. At any height in the red column, there is more air above my head than at the same height in the blue column, therefore the pressure is greater. The answer number 1 is backwards in terms of thermal expansion of air. The blue column expands taller than the red column, so that's wrong. The balance of forces is right, but the fact that the blue column expands is wrong. So the arrow in the top panel is consistent with how I've drawn the two columns of air, but the point is the two columns of air shouldn't have those heights. The blue column should be short and the red column should be tall. In 3, I've got the heights of the columns right, but then I get the direction of the pressure gradient force wrong. Question C. Height contours are plotted on the 500 millibar upper air chart, which best describes the physical situation. So I again have 3 panels. Figure 2b, I show a warm region and a cold region. I draw a line showing the height contour for the 500 millibar pressure, and I have an arrow showing the pressure gradient force either going from cold to warm or warm to cold. The correct answer is 1. The pressure surface is higher in the warm column and lower in the cold column. There is a pressure gradient force from the warm region to the cold region, and it is the upper panel that is correct. The reason for this comes from question B, that at a given pressure we are higher in warm columns than cold columns, and conceptually the idea that the wind blows downhill as we experience things on the surface of the earth moving, they roll downhill. And so this all fits with our conceptual ideas of how we understand things operating under gravity. That's one of the reasons that this method of looking at pressure gradient forces is used in meteorology, that it fits conceptually what we know from life on the surface. The other 2 answers in 2, I've got the heights wrong. I've got that the cold isobar is at a higher altitude than the warm isobar. The pressure gradient force in this case is consistent with the heights, but the heights are inconsistent with the temperatures. And in 3, I've got again that the heights are inconsistent with the temperatures, and then adding insult to injury, I've got the pressure gradient force backwards. Question D, and please excuse the phone call that occurred at the end of question C. An air parcel starts to move from rest between two isobars in the northern hemisphere. This is figure 2C, which best describes the motion of the air parcel. I'm just going to read the correct answer before turning the page to look at the diagrams. The air parcel starts moving from the high pressure isobar to the low pressure isobar under the pressure gradient force. The Coriolis force deflects the parcel to the right because we're in the northern hemisphere. As the speed of the parcel increases, the Coriolis force increases, turning the parcel further to the right. Eventually, the Coriolis force balances the pressure gradient force. Under this balance, the parcel moves to the right at constant speed. And I'm going to turn the page to talk about that on the diagram. So the correct answer is the left panel. I want to talk about some issues here about the balance of forces. The pressure gradient force stays constant because it's based on the pressure difference, in this case 8 millibars, across some distance, maybe several hundred kilometers. And so that pressure gradient remains constant in the problem. These winds that we're talking about that run between isobars are called geostrophic winds, earth-turning winds, because they are turned by the Coriolis force, which is the force due to the rotation of the Earth. It's not a true force, it's a way that we deal with the fact that the Earth is rotating below the wind above it, and we deal with that as a force. It's the Coriolis effect, which we manipulate or account for as the Coriolis force. So in this problem, the parcel, if there was no Coriolis force, would just move from the high pressure to the low pressure. But as its wind picks up, as it speeds up under constant acceleration of the pressure gradient force, its velocity increases. Therefore, the Coriolis force has to increase. Eventually, we get to the point that the Coriolis force operating to the right has turned the parcel to the right, and therefore we have a wind which is perpendicular to the two forces. So at that point the wind neither increases nor decreases because there's no acceleration in the direction of the wind. And so the wind continues along like water between the banks of a river, flowing parallel to the banks, parallel to the isobars, with two tugging forces, the pressure gradient force moving in one direction and the Coriolis force trying to move it in the other. They are in perfect balance, and so the wind just continues at constant speed. If we go back to Newton's laws, if a parcel is not, or a body is not under the influence of a force, it will either stay at rest or continue at constant speed. And so once the orientation of the wind and the forces is such that the forces are perpendicular to the wind, there is no component of the force further accelerating the parcel, and the wind neither increases nor decreases. In the middle panel, I have that the Coriolis force doesn't turn. So that's the mistake that's here, and therefore the wind should never turn. What should happen in the middle panel is that as the Coriolis force grows, it should just counteract the pressure gradient force, and you would get to some odd situation of the wind stopping. But there's nothing to cause the balance of forces in the middle panel would not cause the wind to move to the right. And in the last panel, I've got everything backwards. The Coriolis force take in the place of the pressure gradient force, and then the pressure gradient force turning like the Coriolis force, and it's just completely wrong. I've got the forces backwards. The thing I want to talk about here that's a deeper issue while I've got your attention is this explains why winds come from the west. In the northern hemisphere, if I have a hot equator and cold mid-latitudes, I have this situation where upward is north and southward is heading towards the equator is down. And in that case, any parcel leaving the equator under the pressure gradient force from the warm tropics to the cooler mid-latitudes will be deflected to the right. And this is why we get dominant westerly winds in the atmosphere in certain regions of the Earth. We'll come back to that when we talk about the general circulation. The answer to question E. An air parcel near 500 millibars circulates around a central low pressure in the northern hemisphere. Figure 2D, which best describes the physical situation? And the correct answer is 2. The inward pressure gradient force is larger than the outward Coriolis force. The net inward force keeps the parcel circulating counterclockwise in orbit around the low. This is an example of circular motion, orbiting motion. The parcel orbits the central low. In such motions, you have to have that there's a net inward force. If you think about putting an object on a string and twirling it, you know that there's a tension in the string, and therefore that is the force that you're providing. Under Newton's laws, if you broke that force, the parcel would just fly off in a straight line. The fact that you keep nudging it around the circle so it's moving around the center is due to the force in the string. In the atmosphere, it's due to a misbalance between the pressure gradient force and the Coriolis force. The pressure gradient force is inward toward the low. The Coriolis force is to the right. Therefore, the parcel moves in a counterclockwise direction in this scenario. And under that set of balances, we have a net inward force giving us the cyclonic behavior. In the panel on the left, I've got the Coriolis force large and inward, the pressure gradient force outward, and I've got the parcel rotating in the clockwise direction. The orientation of the motion clockwise is consistent with a force to the right, the Coriolis force in the northern hemisphere, but I've reversed the pressure gradient force. The pressure gradient force in this case is outward, and it should be inward to the low. So that's why the left panel is incorrect. And in the right panel, I have made the direction of motion inconsistent with the Coriolis force. So the pressure gradient force is in the right direction, the Coriolis force is in the right direction, the net inward force. Remember, when I'm talking about forces here, the strength of the force is given by the strength of the arrow. So the inward force in all these diagrams is a little bit larger than the outward arrow, the outward force, giving me a net green arrow inward when I look at the balance of forces. The winds around cyclones and anticyclones, these circular winds, are called gradient winds, different from how we've talked about geostrophic winds in question D. The reason that we have a different name for them is that in geostrophic winds we get a perfect balance between the Coriolis force and the pressure gradient force. In gradient winds we have an imbalance between the pressure gradient force and the Coriolis force because we have to maintain the objects in circular motion, which requires a net inward force. We now move to question F in problem 2. Question F. The following questions refer to figure 2e. The figure shows the three forces: pressure gradient force, frictional force, and Coriolis force acting on an air parcel over land at 40 degrees north, and the velocity of the air parcel, the wind, at the surface. So we're now down at the surface at pressure of about 1,000 millibars. So friction matters because we've got the surface friction of the ground. In the earlier questions in this problem, we were at 900 millibars, which is about a kilometer above the ground. We were at 500 millibars, about 5 kilometers above the ground, and we didn't consider friction. So now we're considering what does friction do in the motion of air parcels. So we're looking at the geostrophic wind at the ground. The first part of this question, 1. Which arrow identifies the frictional force, FF? And the answer is C. The frictional force is the arrow to the lower left. The frictional force is always opposite to the velocity or wind direction. And so in this case, C is opposite A. A and C are the only pair of arrows that are directly opposite each other. The other way to look at this is looking at the pressure gradient. You know the pressure gradient force has to go from high pressure to low pressure. So D has to be the pressure gradient force. Frictional force has to be opposite to the wind, and the Coriolis force has to be either to the right of the wind in the northern hemisphere or to the left of the wind in the southern hemisphere. In this particular case, the only option is that it's to the right of the wind, that it's B, and therefore we are in the northern hemisphere. So think through what you know about the direction of the wind and the various forces, and you can parse out in any example how the geometry fits the example I give you. 2. If the air parcel moves from land to water, which force changes? Well, if the pressure gradient doesn't change, then if only the surface changes, then the friction changes, and the friction becomes less over water than over land. So the answer is C, the frictional force changes, FF. The strength or magnitude of this force decreases because the friction is less. If the parcel moves from land to water, does the wind change direction? And the answer is yes. And the reason why is that if the friction decreases, then the wind speed increases. If the wind speed increases, the Coriolis force increases. So B increases and A increases. If B, the Coriolis force increases, it pulls the parcel more to the right, and so the parcel turns counterclockwise and the parcel increases in wind speed. 4. If the air parcel increases in latitude from 40 to 65 degrees north, which force changes? And the answer is B, the Coriolis force changes. Remember, Coriolis force increases with latitude and it increases with wind speed. It also increases with rotation of the Earth. We can't change the rotation of the Earth. We are looking at if the wind were to stay the same and we were at higher latitudes, then the Coriolis force would be larger. And so the Coriolis force would increase. 5. If the parcel increases in latitude from 40 to 65 degrees north, does the wind change direction? Well, if the Coriolis forces are going to be larger, then they're going to pull the parcel to the right and counterclockwise. And so we would expect the wind direction to change. The last question, does the wind speed increase, decrease, or stay the same? This comes back to the question we talked about hurricanes in the Arctic regions. And this is becoming a little complex because now we're considering latitude change and wind speed change. But to first order, because the Coriolis force is larger for a given wind speed at high latitudes, you need, therefore, a smaller wind speed to balance the pressure gradient force through the Coriolis force. So a smaller wind speed gives you a larger Coriolis force, which can balance a larger pressure gradient, or for a given pressure gradient force, a smaller wind will give you the Coriolis force you need, and therefore at higher latitudes for the same pressure gradients, everything else being equal except the change in latitude, you expect to see lower wind speeds. Question G. Figure 2F shows a parcel orbiting a high pressure system or an anticyclone in the northern hemisphere at 500 millibars. The parcel is in orbit at A, but then, magically, nudged out of orbit at B and returns to orbit at C. Explain the balance of forces and motion that explains why this happens. For full credit, label the arrows on the figure. So the point of this problem, and I discuss it below, but comes back to why do cyclones and anticyclones persist over several days or even maybe over a week in the atmosphere? Why don't they just fall apart the first time they're disturbed? So this really speaks to why weather systems persist over time. It's a very important question about the weather having some order to the weather, that it's not just random chaotic motion all the time. And so if we look at this diagram, it's a high pressure system, so the pressure gradient force will always be outward, radially outward, a line from the center to where you are heading straight out. And so the pressure gradient force is the red arrows in this case, outward from the central high. We're in the northern hemisphere. The Coriolis force, if we're orbiting clockwise around the high, the Coriolis force is going to be to the right. So the parcel at A shows the balance of forces and the wind that we expect for an anticyclone. If I nudge the parcel at B, I take the parcel at A and magically put it at B, I have upset the fundamental geometry as follows. In A, the pressure gradient force and the Coriolis force are at right angles to the wind. The wind is moving at constant value. The wind speed is constant as the parcel orbits the high. Now when I move out to B, the pressure gradient force is no longer at right angles to the wind. It has a component perpendicular to the wind and it has a component parallel to the wind, a vertical component on the page and a horizontal component on the page. And therefore we now have the pressure gradient force can actually accelerate the wind. And so it does. The nudged parcel would speed up, moving to the right in this case. If it does, the Coriolis force has to increase. And if the Coriolis force increases, we are pushed downward to the right of the wind and we're brought back on orbit at C. So the idea here is that if I take a wind parcel and try and move it off orbit, it will try and move back on orbit. And that's why we call it stable, that the orbital motion, if it's disturbed, tries to restore the orbital motion of the anticyclone. And so this is what we're trying to show in this problem. And so it speaks to the issue that cyclones and anticyclones are fundamentally stable once they get set up. You'll notice in the picture that I've made the Coriolis force arrow longer than the pressure gradient force because there has to be a net inward force holding the parcel in motion. And again, the topic that I'm asking you to reach for here is the force concept, that a force can have components, just like a position can have components. You can walk directly in some direction, or you can walk north for some distance and then east for some distance and get to the same place on a grid system rather than walking in a straight line. Well, in B, the pressure gradient force, the straight line arrow is radially outward from the high pressure system, but that can be decomposed like on a grid system to a vertical component and a horizontal component. The horizontal component of that force manages to accelerate the wind because it's aligned parallel with the wind, and therefore the Coriolis force has to increase, comes into play, and restores the parcel to C, where it's back on the orbit, and we have a restoration of the anticyclone winds. The final question in problem 2H. Small aircraft use altimeters that sense the local pressure to determine the altitude of the aircraft. If a pilot follows a constant pressure from standard temperature to lower than standard pressure, will the plane have increased or decreased in altitude? Briefly explain why, and discuss why aircraft flying near the ground are prohibited from flying at extremely low temperatures in Alaska. The first point is to answer the first question mark in the question. The pilot will have decreased in altitude. That was the first question inside this question. That we saw earlier in this problem that in cold air, pressure surfaces are lower than they are in warm air. The second part is pressure surfaces are at lower altitudes in cold air than warm air. Thus, if an altimeter uses a pressure measurement to estimate the altitude, it will have the pilot fly at lower altitudes in cold air and higher altitudes in warm air. In extremely cold conditions, a pilot can end up flying significantly lower than their altimeter reports. And as a result, if a pilot is flying close to the ground, if they're attempting to land or they're going on short trips, they may actually be lower than they think, and they may hit a tall structure, they may hit a hill, or they may come into land and hit the ground sooner than they expect. In either case, there can be an accident, and therefore there can be essentially bans on flying in extremely cold weather. 60 below weather in Alaska can result in pilots just being grounded.